This is the second of our 6 videos that we will do for Chapter 4. We've already looked at force causing acceleration. I've already reminded you to keep an eye on your vocab words. We're going to move ahead into a special situation of force being friction. So let's talk about friction. We've actually talked about friction off and on. You're familiar with it. We've talked about it in the experiments and demonstrations we've done in class. Let's put a little bit of definition behind it. Here's the first thing that you look at is that friction is actually something that's happening on a very localized or almost even sometimes a subatomic material. It's the fact that two surfaces will interface with each other, and as we press down, in fact, we magnify the effect of the friction between the two surfaces. This is one that we will put some numbers against, and it gets to be kind of interesting. We can talk about the stickiness of the two surfaces or the slipperiness of the two surfaces. And this is something that you are familiar with in everyday life. If we've got a rough crate on a wooden floor, it's going to be more slippery than that crate would be on a rough floor. Common sense, you've dealt with this anytime that you have tried to move boxes or furniture. You are well aware of friction. Let's put this to the test. Does friction occur only with sliding objects? Does friction occur in water? Does friction occur in air? Does friction occur in all of the above? What do you think? What do you think? Well, the truth of the matter is that friction can occur in all of those situations. It's not necessarily solid surfaces that are rubbing together. It's the atomic nature of two materials rubbing together. All right? Another thing to keep in mind is our objects at rest, maybe the reason they are at rest is because of friction. When you have the situation that you have a surface with something on it, and you can apply a force, and maybe the object doesn't move. All right? And why would that be? Is that inertia? No, that's just telling you that your force is not big enough yet to counteract the opposing force of friction. Let's move on. Let's look at another example. Here we have our friend Sanjay, and Sanjay is just barely moving a refrigerator box. He's strong enough to move it, that he's getting some motion, but it is not accelerating. So he's moving it slowly. He's pushing it across the kitchen floor at a constant speed. Constant speed. What does that tell you about the force of friction? Does that mean that the force of friction is less than Sanjay's push? Are these two forces equal? Is friction equal and opposite to Sanjay's push? Is friction greater than Sanjay's push? All right, think about that for a minute. Again, the key point is that Sanjay is pushing at a constant speed. All right? I need to check some math. Well, in this case, we've got Sanjay pushing this way, and the force of friction is acting opposite of him. So in this case, considering that, remember that the point of reference that we're looking at right now is that the refrigerator is moving at a constant speed. So we're not talking about the situation where he got it to go from rest to moving. That happened a while ago. He is maintaining a constant speed. So when he's pushing this at a constant speed, it's telling you that the two forces are in equilibrium, that he is pushing just the same amount as the force of friction, but not enough to make the refrigerator box accelerate. The acceleration here is 0, so the forces are balanced. Okay, Sanjay has had his Wheaties, and now he's pushing the refrigerator against the floor at an increasing speed. All right? So his push is enough to counteract the friction and cause the refrigerator to have a lot more speed. Okay? In this circumstance, is friction less than Sanjay's push, equal to Sanjay's push, equal and opposite to Sanjay's push, or more than Sanjay's push? What is the friction relative to the push that Sanjay is making? And the key word to this is that the speed is increasing. Well, when we have the situation of an increasing speed, then we know that there's an acceleration involved, and that the frictional force is less than the force at which Sanjay is pushing. So our net force is greater than 0, and the refrigerator is no longer in equilibrium. That's a hard thing to remember. Equilibrium, we understand when equilibrium is something is not in, when our velocity is 0, when our speed is 0, it's pretty easy to understand that something is in equilibrium. When our speed is constant, then it's a little bit harder to wrap your head around that something in constant speed is at equilibrium. We're going back to Newton's first law then, that there's no net force. All right, our next thing that we're going to talk about in the next video will be the difference between mass and weight. See you then.